Thanks, Wes. Good afternoon. Yeah, this afternoon I'd like to talk about how we're taking the combination of SMPTE2110 and PTP and changing virtual production and virtual production stages, and specifically in relation to the virtual production technique of in-camera virtual effects. The genesis of this talk comes from work that we've been doing at NVIDIA with the combination of Epic Games and the Epic Unreal Engine and Megapixel VR, who make the Helios LED wall controller that's commonly used for the LED volumes for virtual production. So, as many of you probably know, virtual production is a new way of creating content for film, TV, live events. It combines a rendered LED wall or LED volume with live action that's captured by one or more cameras on the set. And the visual effects are then added in the camera. That's why it's called in-camera virtual effects, versus like in a traditional virtual set where you have a green screen or a blue screen and you do a chroma key. In that case, all the reflections and adjustments in the background imagery are added during post, where in-camera virtual effects or ICVX, the LED volume takes care of this for the most part, giving you the accurate lighting and a more realistic world that gets composited right inside the camera. So before jumping into how we're using 2110 and PTP on set, let's just make sure we understand a little bit more about the lingo of virtual production. So here we have a picture of an LED volume, courtesy of Epic Games. It's their lab stage down in LA. So we have an LED wall. So it's out of LED tiles driven by LED wall controllers, and each channel of the LED wall controller is driven by a render node that includes a GPU from NVIDIA, as well as a network interface card or a NIC card. So the interview frustum is what the camera sees, and it's rendered at a very high resolution, and it's tracked by the camera as the camera moves across the set. And that's typically where your live action would also be, right in the camera. So in this picture here, you can see that we have the two inner frustrums here that are tracked by the camera. And then the outer view frustum is like the background plate on the wall and the lighting. And these are typically rendered at a lower resolution, one, because they're off camera, and two, you want to save the resource. If we rendered the whole volume in a super high resolution, it would take many more resources in the render nodes that are really going to waste because they're off camera. So then the render nodes composite the live action of the inner frustum with the lighting effects provided by the outer frustum to give you the final shot. So in a traditional virtual production stage, like I have here in a diagram, we have two cameras. We have our LED wall here, driven by 4 render nodes going over using DisplayPort or HDMI into the wall controller, which then drives the LED displays. And then we have our 2 cameras, each connecting to a CCU, typically via SDI. And then in this case, each CCU sends the frustum data for the inner frustum to the render nodes, and each render node has 2 GPUs. One GPU is simply rendering the inner frustum at a super high resolution, and then that gets composited on the second GPU. It gets transferred over what we call SLI or NVLink to the second GPU, where it's composited with the background plate and the lighting and all the effects are added. So in this scenario, we have 2 GPUs, and we always have, and each render node renders the inner view frustum of every camera. And then once the final scene is rendered, it like I said, the render nodes drive the display controller through traditional HDMI or DisplayPort. So the problem with this setup is that it doesn't scale. It works okay for 1 camera and maybe 2 cameras, but the more cameras you add, you have to reduce the quality of the rendering of the inner frustum because you need to render it before you can composite it with the outer frustum. And another drawback of this is there's some complexity in the transfer of the high quality rendered inner frustum over from one GPU to the other over SLI. That, I mean, it's not difficult. It's just another thing that the application needs to do. In this case, the Unreal Engine. And in this traditional stage as well, everything is synced together with a traditional blackburst house sync signal. So what happens when we go to 2110? So here's what it looks like with 2110, where everything basically connects to the network switch. We've eliminated the SDI. The CCUs are really just additional render nodes. In this era that we're in, where everything's becoming a server that's built on common off-the-shelf or COTS hardware that incorporates a GPU and a NIC and an Intel-based server running Linux or Windows or whatever. In this case, the CCUs are just two more render nodes, just like all the other ones. So the cameras connect through the switch to the CCUs, and each, now you have a CCU that renders the inner frustum, rather than, so now the render nodes that render the wall only need to have a single GPU, and the render nodes for the cameras, or the CCU render nodes, are rendering simply the high quality inner view frustum for the camera to which they're assigned. And then these high quality renders are then multicast through the beauty of SMPTE Video over IP. We can render the inner view frustum once and then multicast it to all the render nodes. And that actually is done at 2x the frame rate, so faster than real time, so we can get it into the render nodes so that they can do the composite and all that at the back of the frame time. So the wall nodes then composite these inner frustums with the outer and render the wall. And then the wall nodes also drive the LED wall panels through the LED display controller with SMPTE as well as wall controllers come onto the market, like the Helios wall controller from Megapixel VR, which takes native 2110-20 video in, and then it drives the wall that way. And in this case, the sync is achieved via PTP. So again, it's over IP. So in a SMPTE virtual production stage, we've eliminated the display port and HDMI and all the issues that we have with that, with cable length. We've eliminated SDI and some of the restrictions around video formats and limitations of 12G, and we're stable. We've settled on PTP as a grandmaster. So we've really simplified all the cabling on set. So I'm sure everyone here knows a lot about SMPTE so we won't dig in here, but currently what I'm talking about is we're using Dash 20, which is the uncompressed active video part. There's many parts of 2110, but we're using Dash 20, but going forward we could use Dash 40 for camera tracking data or Dash 30 for audio. I mean, there's lots of extra things to do here, but at the moment we're just using Dash 20 for video, both to drive the LED wall controller and also to multicast the inner frustrums to the render nodes. And ideally from the camera as well, if you look at a solution like Red Connect, where they have IP coming out of the camera now, you can go right into the switch with your R3D right out of the camera and do the debayer and all the processing on the camera CCU nodes. So just in summary, SMPTE really simplifies the infrastructure on a virtual production stage. And like I said, we're currently only using it for video, but there's other things we can do with it going forward. And ultimately it scales because now we can render because each inner frustrum is rendered on a CCU node, we could actually do higher resolution CCU inner view frustrums, because we can throw multiple GPUs at an inner view frustum now, which we couldn't before. So we could partition the rendering to actually produce higher quality rendering and also go above 4K, which is typically the limit of view frustum, interview frustum rendering today. So moving along to how we use PTP in this environment. So again, PTP is from IEEE 1588 or SMPTE 2059 specifications, where you have a global time that's nanosecond based that comes over the IP network to all your devices that are connected. So they're all synchronized within nanoseconds. So virtual production really wouldn't be possible without synchronization, because you have cameras, you have tracking gear, you have displays, you have GPUs. Everything needs to be synchronized to ensure that the correct photons are emitted from all the displays and captured at the exact correct moment by all the cameras in the scene. As soon as something's out of sync, then the whole infrastructure breaks down. So to achieve this, there's multiple areas within the scene or the flow where you need to have synchronization. And the first is consistent PTP timing between all the render nodes and the camera control nodes. And so it's not difficult to set up PTP on these nodes. However, just setting up PTP doesn't guarantee you that all the PTP followers will behave identically, because there's difference in the PTP stack mutations. There's the CPU can interrupt the PTP stack thread and cause delays in the processing of PTP messages. It can be easily misconfigured between the NIC and CPU. There's hardware timestampings with different resolutions and routing methods, and of course there's different operating systems capabilities. Like for example, with this example here, we're using Unreal Engine, which really runs on Windows, and on Windows there's really not a good PTP solution. So how do we solve this problem? So we solve this problem by using a DPU, which is a system on a chip programmable processor that's on a network card. So it combines a high performance multi-core ARM CPU with a traditional 2500, 200 gigabit internet network interface, capable of processing and efficiently transferring all the data at line rates to both the GPUs and the CPUs. And then it also has a rich set of programmable accelerator engines that we use to offload and, in general, improve the application performance. And while the DPU in other application areas can be used as a standalone embedded processor, we're using it here on a smart NIC, what we call a smart NIC. So it's a network interface card basically with a little CPU on it that's running in Ubuntu OS. And so what do we use this for? Well, we use this to deliver the accurate PTP timing. And it works not only for, in our case, we're using Windows, but you could use it on Linux, and it works virtualized as well, and you get the same timing, whatever the platform is. So in this case, the PTP 4L stack runs in a Docker container on the ARM cores here. The NIC hardware receives the PTP messages from the network and passes them to the PTP 4L stack, and then updates the PTP hardware clock, and then the applications then call into, in our case, the RiverMax SDK, which is used for the 2110 implementation, to read from the PTP hardware clock to get the PTP clock. And like I said, because you can take the smart NIC or DPU and put it in a virtual machine or in a hard bare metal machine, it performs the same. So how does this look on a virtual production stage? So typically you have at the top we have our LED wall. Then underneath it we have our LED wall controllers, and we have our network switch. And along the bottom we have our render nodes, each with a GPU, a sync card for the GPU, and one of these DPUs. So the sync card is a card that we make that attaches to the GPU and controls the timing of the GPU to lock it to an external sync. And traditionally, we've done this using a house sync, but now we have a technique to lock this to the PTP time, which I'll talk about in a second. So if we take the setup here, all the display tiles must be temporally aligned such that every tile shows the same frame at the exact same time with the same scan out. Otherwise, if they don't all update simultaneously, you'll have tearing and other temporal artifacts, right? In addition, so that's on the display side. So that's PTP will solve that for us. And in addition, the GPUs must be timed to PTP so that they update to the next frame to render at the exact frame time determined by PTP as well. Otherwise, if all the render nodes are out of sync, then you have, again, temporal artifacts, which the LED wall controller is totally can't control at all because it's just getting the frames from the render nodes, right? And at the same time, which not really in the photo here, your camera render nodes that are rendering also are synced to PTP. So on the GPU side, and then for the scan out of the GPU, but also in the PTP wall controller, the hardware piece of this is what we call raster lock. So it's locking all the scan out to the sync provided by PTP. So on the left, we have 3 displays, and it shows like if you have a moving object going across the displays, in this case, it's just a simple vertical bar. If display 1 starts at time t1, but then display 2 starts at some time past that, while display 3 starts at some time previous to that, then you have this tearing, right? So with raster lock provided by the sync card and ultimately the PTP clock, we can lock the raster scan out of the GPU so that all the displays attached are synchronized, and this would be the same way it would work in the wall controller. So that's kind of in the display / hardware side. On the application side, to guarantee that all the GPU render nodes are rendering at the same frame, an application must use present groups or present barriers. So present groups is when you have a bunch of GPUs, or you have a present group is to lock all the windows on a single GPU. So on a single GPU, you can have 4 displays. So you would lock all those displays using a present group across the single GPU, all the windows or full screen views. And then to lock all the vertical retraces across all the render nodes in the cluster, then you would use what we call a present barrier. So how does it work? Well, in the picture here, we have 3 GPUs and 3 render nodes. And because they're rendering different quadrants of the scene, the amount of time it takes to render may be different because there may be more or less scene complexity. So the render time varies. So if we don't lock it, then as soon as they finish, they swap and update. Well, so using a present barrier, we lock it till they're all done, and then when the slowest one is done, then it triggers the present barrier to swap and then display all the same frame from all the GPUs simultaneously. And also in the picture here, you can see where GPU 3 took more than a frame time, so we actually missed a frame, but because all the other GPUs had to wait until GPU 3 was done. So this is how in an application we synchronize all the displays. So how do we generate the frame sync from PTP? So we start with our PTP Grandmaster, and then from the NIC card in the firmware of the NIC, we have the calculations, and we also have, of course, the RTP header and the marker bits for the frames. At the PTP time, we can calculate from in the DPU core how far we are, knowing the frame rate and the resolution. You can tell from the epoch and the time exactly how far you are in the frame. So you can tell where the start of the frame is. So what we do is from the network card, we can send a pulse signal from the network card through a loop cable to the sync card, and then that sync card drives the vertical retrace and the swapping of the back buffer and the front buffer on the GPU. And we can actually do this at a much higher, where we used to always do this in traditional virtual sets with Blackburst Sync. Now with PTP, we can actually do it at much higher frame rates, up to 120 hertz frame rates. At least that's as many as we've tested at this point. So that's my presentation today. And like I said, I'd like to thank Epic Games and Megapixel VR for helping with this presentation. We've in Epic Unreal Engine 5.1 and soon to be 5.2, they have the SMPTE2110 plugins available that you can download and use. I'm working with them now on 5.2, where we're adding some additional features. And 5.3, there's actually some additional other stuff that we're adding. And like I said, Megapixel VR Helios is available now, and it takes 2110 native input to drive the wall controllers. And yeah, without them, I mean, working with them is how we built this presentation. So thank you.
We have a microphone here. Sorry. No worries. Okay, thank you, Thomas. We have a question here.
So my question is about the PTP sync via the frame lock cards. I'm used to the regular end display workflow where you take house sync into one of the cards and then daisy chain frame lock out of them for the rest of the nodes. When you do the PTP version of that, do you recommend having one machine process the PTP and then go frame lock out of the cards in each cluster?
Yeah.
And do you need to connect the DPU to the frame lock card, or how do you do that part? Because I have a machine with a DPU that I'm like testing with, but I don't actually know how to get hardware frame lock working with it.
Yeah, so let me, so the first part of your question is, I think, yes, you want to, with traditional Blackburst today, with your end display, you're just using the Blackburst from one node and going, you still want to do that with PTP. You don't want to have all the DPUs doing the calculation of the frame time because you're adding more variables than you need to add. And then for your second question, the newer, we have a SKU of the Bluefield 2 DPUs that have little BNC connectors on them that then loop into the Quadro sync card. And that's how we get the sync back into the sync card, then into the GPU. Yeah, but the firmware supports, the current firmware supports all the soft, has all the support to generate the frame sync. It's just you need to have a Bluefield 2 DPU that has the little connector on it.
Okay, great question. Any other questions?
So what can you reiterate? I'm sorry if I missed some stuff because that was great. But what exactly is running on the DPU? Is that, and where is RiverMax running in the system? I'm always curious about where exactly the conversion from traditional video into the IP signal, is happening.
Sure. So so in the case of the Unreal Engine, they're rendering in DX12. Yeah. So instead of using an SDI plugin to go to SDI, they're by capturing the frame, basically it renders off screen, and then you either transfer to a traditional SDI plugin, or in this case, we're transferring it into a buffer that then gets handed to the NIC through RiverMax to go out as 2110. Okay. So it's
that buffer is just like a raw buffer that the data is just coming over.
It's the pixel data, and sometimes depending on what. There might be a color space conversion from RGB or YCBCR or whatever, but yeah, it's. Is
that a custom layer there, or is that is that what RiverMax is doing in that?
It's context? I mean, RiverMax, it's just data.
Yeah.
It doesn't know about pixel formats and all that, so you just give it a pointer and say DMA the data from here. So there's a custom layer in Unreal Engine that does well, it's the same layer that they use for SDI, but they're just giving the buffer to RiverMax instead of giving it to the Decklink SDK or AJA SDK.
Got it. Okay.
What was the second part of your question? The timing container.
Like oh, yeah.
So the timer container is it's a Docker container, and if you're familiar with the NVIDIA website, we have what we call NGC, which is a container library where you can download containers for supercomputing applications and all other things. And it's on there, and you download it, and it runs in Docker on the little DPU, and that's how it does it. At the moment it is, but the DPU could be used for so many other things that we don't use it for now. It's just, we're kind of just getting started. The funny story is that we had a hackathon, and running the PTP in a Docker container came out of a hackathon that the networking group in Israel did, and that's how it came to be. So now we're working to add other functionality into the DPU for like security, and it can do a lot of things, but it just hasn't come to life yet, and it's not always applicable in this space. So yeah, yeah.